Hello, welcome back. Today we do shortest path algorithms and we will cover two classical shortest path algorithms, which is Dijkstra and Floyd-Warshall. In Dijkstra, we'll be actually talking about how to go from one vertex to any other vertex of a particular graph in the shortest cost manner. And likewise, for Floyd-Warshall, we'll be talking about how to go from any vertex to any vertex in the shortest manner in terms of cost. So that's what we will do. We are actually attacking this portion of the syllabus on your module 3, which is shortest path algorithms. We would have just network flow algorithm left in order to cover and complete this module. As discussed, we'll do single source shortest path, which is the Dijkstra algorithm, or Dijkstra as they call it. So it's pronounced as Dijkstra, Dijkstra, and this is called as Floyd-Warshall. So these are the two algorithms we'll be covering, and of course we'll be doing a whole bunch of questions. So before we start off with this, let me explain what the Dijkstra algorithm is all about. So we are saying that, let's say here we have Mumbai, and Mumbai, on top of Mumbai, let's say somewhere here is Gujarat, or for that matter you could take Ahmedabad also rather than taking the name of the state. Doesn't matter, it's just a place that I'm trying to convey. And here let's say there is Karnataka, and here let's say there is West Bengal. Now I know that Mumbai is connected to Gujarat and the distance is somewhat, let's say 600 kilometers. To Karnataka the distance is somewhat, let's say 700 kilometers. From Karnataka to West Bengal I can actually go with let's say 2200 kilometers. And from Gujarat to West Bengal it will be somewhere close to 3100 kilometers. I'm just taking rough estimates. Now if I say that starting from Mumbai, can you tell me what is the shortest path to go to Gujarat? You will tell me go like this, 600 kilometers. If I want you to tell me what is the shortest path to go from Mumbai to Karnataka, you will tell this, go like this. But then can you tell me from Mumbai to West Bengal which will be the shortest path? Will this be the shortest path or will this be the shortest path? That is what Dijkstra tries to solve. This anyway looks easy, 3700 as compared to 2900, so go like this and you would reach the shortest path from Mumbai to West Bengal. So starting from Mumbai, we will have to find out how we can go to Gujarat, what will be the cost of it, and what will be the path of it. Right? So that is what the problem is all about. And then starting from Mumbai, our start position will remain the same. How do we go to Karnataka? How do we get the cost? How do we get the path? Similarly, we'll do it the same way for Mumbai to let's say Mumbai, Gujarat, Mumbai, Karnataka, Mumbai, West Bengal. So this is what we will try to solve using Dijkstra algorithm. So this is what is, in a nutshell, what is Dijkstra algorithm. So we'll take a graph like this and let's solve this. So we'll have to assume that we will again we can start with any vertex here. So we will assume that we will start with the vertex which is in chronological order of the alphabets or in chronological order of the numbers. Not that it is a hard rule, but it is a best practice. Now if I say that if I have to come to A, like let's say I'm starting from A, instead of that take a step back and start from here, right, which is very close to A. So if I have to come to A just from outside of A, I'll be crossing a distance of 0, right? So I'm at almost A and I'm coming to A, which means I'm at a distance of 0. So why am I saying that? I'm going to say that from A, what are the shortest ways in which I can reach B, S, D, C and E. That is what I will try to achieve. So to do that, I will also say that I'm also trying to reach A, and I will assume that I will reach A with 0 cost because I'm just outside A, and the rest I will assume that because I'm outside, right, I'm at this point, I am at this point is not connected to any of these points, right? And hence all these points are at infinity distance from that particular point from where I can get into A by crossing it just at 0 distance. Therefore, when I actually do this, I will say that my selected vertex will be the minimum vertex which is in this particular row, and because this particular A is now selected, I will not do any further operations on this particular column. Now what am I trying to do? This is a greedy algorithm first of all, and I'm trying to select the shortest distance in a greedy manner at every stage, thinking that the minimal optimal solution will give me the maximal optimal solution of the bigger problem, right? So that way, now that I have selected A, I am now trying to say that from A, can I go? What are the areas where I can go? From A, I can go to B, which is at a distance of 9, and S, which is at a distance of 6. So I will write here that from A, I can go to a distance from under S. I will write that 6, right? And when I'm writing that 6, I will have to be careful. Why am I writing this 6? There are 3 values that are involved here, and those 3 values is what you see here. So what is the distance of U? The distance of U right now is at a value of 0. So what am I saying is that in order to reach A, I will take 0, and then I will take 6 from the graph, which is from U to V. So if I say this is U, this is my V, then this is my weight U to V. And if this is less than the current distance, which is infinity, right, which is less than the current distance that is there in the immediate above row, the distance of V that I could have gone from that vertex A, then I will select this particular summation as the new summation, and that's how this 0 plus 6 actually lands up here. So it is not just putting this blindly here. You will have to take a plus of what was selected, the cost of that, plus the weight of that, and then compare with the previous row, same column, and accordingly you will get this minimum of this. So I'm going to say that this is going to be the minimum of these values. So I hope you have understood. Let me go through this again. You will understand. So I have gone from A to S. I will go now from A to B, right? So there is one more way I can go. A to B is 9. 9 plus 0 is 9. And then 9 and infinity minimum is 9. The rest, there is no path. From A, there is no other path to go to C, to go to D, to go to E. There is no other path. So I will put infinity there. Right? Here also what I am doing is infinity plus 0 is infinity. Comparing it with infinity, taking the minimum of it. Infinity plus 0 is infinity. Comparing to infinity, taking 0. Infinity plus 0 is infinity. Comparing with infinity, taking it as infinity. I hope you are now getting a hang of it. Now here, what is the minimum here? The minimum here is S. So I will select S. I will mark this entire column as taken, and I'll say that S is already visited. Right? So I'll say S is already visited. Got it. So this is done. Now, since I have selected S, from S, where all can I go? I can only select these. I will not go to S. From S, I will not go to these because these are already blocked. That's why I put this arrow. I will not go back. Right? So I can only go from S to B, C, D, E. From S, can I go to D? Yes. Okay, D takes 8. So what I'll do is, at D, I will put 8. But then the S cost itself was 6. So I'll have to add. So this is this is becoming is the distance was distance to go to S was 6. Add it to the cost on the graph, which is 8, and it is less than infinity. So 6 plus 8 is 14, which you will put under D. I hope you are understanding this. 6 plus 8 is 14. So I took this, I added this to this, right? And then I compared it with the top row, took the minimum of it. So that's my 14. Now, can S go to B? No. So I will keep it the same, because B was already calculated as a minimal figure from infinity. I will not change that. If I cannot change the top row, I will keep it. Acha, you can also imagine it as a mathematical formula. See, from S, I have to go to B. I have to populate this. So from S, can I go to B? No. So then what is the cost? Infinity. So infinity plus 6 is infinity. Minimum of 9 and infinity will be 9. So with that formula also, you can decipher that this will be 9. Right? Anyway, you might want to just imagine the workflow of the formula rather than applying the formula every time. And that's what I'm trying to do. I'll like mix and match both the things so that you choose whatever is convenient for you. Now, S can go to C? No. S cannot go to C, so this will be infinity. S can go to E? No. S cannot go to E. What is the minimum here? 9. So I will select my B and I will block this particular column. From B, I will now go to C. From B to C is 12. But the cost to reach B is 9. The cost to reach B from where? From A. The cost to reach B from A is 9, right? So that's where each row is representing the cost to reach that particular row from its previous vertices. Now, when you are at 9, this 9 has to be added to the cost. What am I going to? I'm going from B to C. So 12. 12 plus 9 is 21. 21 is less than infinity. Then I'm going from B to D. B to D, not possible. Infinity. So the 14 will stay. B to E, not possible. Infinity will stay. Minimal is 14. Minimal is 14. So I will take this, put it down, right? And then what I'll do is I will select this D, right? I've selected this D. And from D, I will see if I can go to C and D, because those are the only two that is left. From D, if I go to C, I will incur a cost of 3. The previous row till D was 14. So I will put 17 here. 14 plus 3 is 17. 17 is less than 21. Put it here. Then I'll go from D to E. D to E is 10. In the previous, to reach D, I had 14. 14 plus 10 is 24. 24 is less than infinity. Put it here. Least is 17. I will mark it like this. And this is done. I have selected therefore C. Now 24. From C, I will go to E. Is 5. So 5 will get added to 24. 5 will get added to 24. And that will be 24 plus 5 is 29. And 29 when compared with infinity will be 29 when compared with 24, because I have already added 5 to 24. Actually not, I'm doing a wrong thing here. I got 5, I should be adding 5 to 17. My bad, brain freeze. So 5 will be added to 17, which is 22. 22 is compared with 24. 22 is minimum. So 22 comes here. This is selected because this is the only minimum column here, and therefore I will say I have selected E. So that is the 50% of Dijkstra done. So now you know that how to create this table. What did this table achieve? This table tells you that to go from A to, let's say, if I start from A and I want to go to A, then I will incur a cost of 0. So I'll come to this A column. I'll see whatever is this block. I'll go down till I get the block. And whatever is that block, I will take the shortest distance. I will put the running path as this, and the actual path will be this. I'll tell you what is running path, what is actual path in the next few rows. Don't worry about it. From A, if I want to go to S, from A, if I want to go to S, I'm just taking it sequentially as it is appearing, right? So from A, if I want to go to S, then my shortest distance, if I see this column, right? If I see this column, then this is 6. So if this is 6, if I found that this is the shortest, this box, if I have found, I will go immediately up. And you remember the n-queen problem, and not the n-queen problem, the knapsack problem. We were trying to see if the top row actually changes values. Here also we will do. Top row is changing values? Yes. Then find out the minimum in this particular row. This particular row's minimum is this. So select that. So my shortest distance will still from A to S will still be 6, but the path that I am getting is I have selected S because I got till S. I went down here, right? I selected S, and then when I went up, I got A. So I selected S and then I selected A. So my running path is this, but actually speaking, I will go from A to S. So that's the difference between running path and actual path. From A, if I want to go to B, then if I go down this, I will see that B is stopping here, which means B is selected, and then if I go up, I will go up till I get to a different value than 9. Here I get that different value. I'll go left, I'll get a box which is minimum, I'll select that. So that becomes A. So this becomes AB. If you see the graph, the shortest way to go from A to B is this, and that's what I have written here. This is the 9. Right, so in this way, if I go on, if I go to A to D, if I go from A to D, A to D is 14 here, right? So I will go up, I will find the difference here, I will go to the left, I will find that, okay, so A to D means I have taken D, I have gone up, and I found that there is a difference here. I'll go left, I'll find the box here, which means that I will select this, which is S, right? So I will select S, and then because I selected this, I will again go up. It's not done, you have to reach till the top. Again I got a difference, so I will go to the left, I'll get A, right? So this I will write as B.Sc, A.S.D. So see the graph, A.S.D is the shortest way in which you can go from A to D with a cost of 14. Right? Then we will do A to C, and with A to C, what you will see is that we have gone from where did we start? Okay, A to C. Let's see this, A to C. Okay, we came here. So this is my C, right? So this is my C. That means I'll go up, I see an immediate change, right? So anyways, I've selected C. Then I see an immediate change, which means I will search for the minimum. The minimum is D, right? So I will take the D. Then I will go up and search for a change. I will get the change here, go to the minimum, which is S. So I will select S. And then I will go up and I'll get another difference here, which I'll select as A. So once you start with D, right, if you get from C to D, always know that you will get DSA again. Right, so that's understandable. You don't need to do it again. So this becomes ASDC, and the ASDC is going to return you with 17. And then finally we have ASBDCE. So if I want to go to E, then I will go here. Then here there is a difference, which means I will take C. So I have already selected E, then I have selected C. Now if you have selected C, then from there you will only get this path. So there is no need to check it, you can just write it directly, CDSA, and then you can write ASDCE, and then you can write 22 here, and that becomes your Dijkstra complete, where from the single pair shortest path. Single pair means the source vertex is the same, the destination vertex are changing. What is the shortest path that I can go from every vertex, from a single vertex to any other vertex? And in terms of the algorithm, if you see, there is nothing much. You will only have to make sure that if you have not visited, then you are only going to check that condition. That is for all adjacent vertex, right, of the array that you are maintaining of the vertices. You will have to make sure that this distance condition which I have shown here is actually taken care of, and if it is taken care of, then you will have to if this is less, that means minimum, right? You are taking the minimum distance here, otherwise whatever is there in the previous row stays. And that's all that is there. If you read this, you'll understand that there is nothing much here. Only thing is you are building the vertices, you are making the distances infinity and then starting it. But the main thing is happening here. Just now I have explained that. In terms of the time complexity, if you see after a particular source is fixed, right? So I will actually be searching for the other rows, other vertices, and those vertices will be having n minus 1 iterations, comparison to find the minimum vertex, right? So I'm trying to find the minimum vertex, which is the comparison to find this particular area. Select the unvisited vertex u having the minimum distance, right? So I'm trying to see what is my unvisited vertices which are having the minimum distance, right? So I'm going to go from here to here, right? I'm going to go down and I'm going to go here, and for this vertices I'm going to find out the value of this 6 or the value of this 9, right? I'm going to find out what is the minimum cost that I incur to go there, right? So that's what this particular line says. And then finally, when I understand the cost, I will have to do this jugglery. That is, I'll have to take the previous one, add it to the current cost, and then compare it with this and this. So there are two steps here. One is you are doing a comparison here, which is the check. And then another thing that you are doing is actually assigning that value. These are the two things that you are doing here. So this is step number 1, which is incurring a cost of which is incurring a cost of this. That is, because you are at n, so you will go from the comparisons that you will do, because the source is fixed. You will have to compare with n minus 2, then n minus 3, then n minus 4, and so on, because first iteration will be with n minus 2, right? Because those two are anyway taken, so you will do n minus 2 comparisons. Those two will be left out, and the rest of when you take that, then n minus 3 will be left out, and so on and so forth. So finally you will have only one left out, which is your node itself. So that way you will have this, which is actually translating to this as far as AP is concerned, right? Now if you apply the formula of AP, you will get this. Now if you see, when we are talking about this particular section where we are checking, there also the same thing is happening. There also this is equally applicable. That is, for comparing the distances also, we are actually going to compare with only the vertices which we have not gone, right? And that is, the first time we would have not gone to n minus 2 vertices, second time we will have not gone to n minus 3 vertices, and so this if comparison will also be taking that amount of time. And then we will have to do this, which is the assignment or the update operation, which will also take the same amount of time, and hence your total operation is 3 times of this. And if you do this asymptotically, you will get 3 by 2 n square, which is order of n square. This is the time complexity of a Dijkstra algorithm. So I hope you have got this. These questions again are from your PYQs. 2 times this has come. I have done it in the same manner. You may want to see this, how I have created the Dijkstra graph, greedy graph, and then how I created the shortest path table. Same way I have done it. Prove that the time complexity of Dijkstra algorithm is order of n square. We have already done that. Write down the Dijkstra algorithm to find the shortest path. We have done that. Prove that the time complexity of the Dijkstra algorithm is 3n minus 2, 3n. That's also something that we have done just now. Write short notes on Dijkstra. I've given it here, and that's it. So we will now get into Floyd-Warshall, but I hope you have understood the Dijkstra algorithm. On Floyd-Warshall, which is basically the all pair shortest path, that is, you can go from any pair to any pair, not that you are stuck on one single pair and you have to go to all other pairs. The Dijkstra algorithm gives you that. That is what we saw. Now we are trying to say that from here, can I go to here, here, here? What is the minimal cost to go there? Similarly, from 4, can I go to 1, 2, 3? So each vertex is the single source shortest path. That means from 1, I can actually do a single source shortest path algorithm to 4, to 2, and to 3. This is from 1 I can do that, right? Similarly, from let's say 2, I can actually go to 1, 4, and 3. And likewise, from 3, I can go to let's say 1, 2, and 4. And from 4, I can go to 1, 2, and 3. So which means that all these are single source shortest path, right? So this is what is single source shortest path. This particular problem we have solved using Dijkstra, right? So Dijkstra, right? I need to be careful on the spelling of this. I hope I got it correct. Okay, so we can solve this with Dijkstra. So how many Dijkstra do we need? We need 4 Dijkstras, right? So we need 4 Dijkstras, which means we need n Dijkstras. Now we know the order of a Dijkstra is order of n square. We need one more order, right, in order to say that, okay, we are going to do that many number of n's of Dijkstra or Dijkstra, whatever you want to call it, order of n cube, and this becomes the order of Floyd-Warshall algorithm. There is another way to draw the order, we will see that, but this is in a nutshell why we are saying that the order of Floyd-Warshall is n times that of the order of Dijkstra. Assuming this is a graph, right, let us see how we can calculate it. Now this is an intensive matrix analysis and calculation, which is why I have not taken an attempt to do it live on the session. It will be a huge lecture if I do it. Normally it does not come. Only 1 year it has come, I think 2011. After that, calculation does not come, algorithm comes, order of complexity comes, and that's it. That's pretty much what comes from Floyd-Warshall. But then it's there in the syllabus, it has come in 2011, we have to see it, right? So we are seeing it. So what we do is, first we represent this particular graph as an adjacency matrix. And you know what this adjacency matrix is, that the row number 1 represents from 1. If I have to go to 1, then I will not incur any cost. From 1, I am connected to row 2. From 1, I am connected to 2 with the cost of 3. From 1, I am connected to 3, I am not, which means infinity. From 1, I am connected to 4 with a cost of 5. This is a directed graph, so it will not be symmetrical. If you see my graph lecture, you will understand what I mean. It is a square matrix, yes, but it will not be symmetrical. If it is undirected, it would have been symmetrical. Therefore, the cost of going from 1 to 3 will not be the same as the cost of going from 3 to 1. So 3 to 1 will have, or 2 to 1 rather, 1 to 2, the cost of going from 1 to 2 will not be the same as the cost of going from 2 to 1. So 2 to 1 will have 2, whereas 1 to 2 will have 3. And this is violating the symmetry. That's why I said it is not symmetrical. Now that's on the graph and the adjacency matrix. So I hope you can create this. This matrix, mind it, will be called as D0 matrix, distance 0 matrix. Now if we have to calculate the next level of matrix, which we will call as D1, the formula of that is this. Don't worry about that. We will see this formula. Before doing this formula, we will take this matrix and create a working matrix first of D1, the matrix that we want to create. By the way, how many matrices do we have to create? We are actually using DP style of programming, right? So we are using a DP style of programming where the initial subproblem costs are getting calculated, right? So we are doing a D0 calculation, we are doing a D1 calculation where D0 calculations will be used. So all the subproblems that are actually getting encountered is calculated only once, stored, and we are referring to that when we need it in a subsequent higher stage. And that's how we solve the optimal problem. And that's what is DP. So in this DP, we are saying that we will take this D0 and we will create an intermediate matrix. In that, all the diagonals will keep the same. And because we are creating D1, so we are going to say that the first row and the first column we will keep the same. So if you see this one, I have kept the same here. And if you see this one, I have kept the same here. The rest of the things I have given placeholders, and this is what the placeholders you will fill. How? Using this formula. So this is your recurrence formula for the DP, and that is what it is saying is, in order to calculate D1 of ij, that means I am going to calculate first this, which means I am going to calculate D1 of 2, 3. So in order to calculate D1 of 2, 3, I have to take a minimum. That means the 2, 3 cell, all the inputs will come from the D0 matrix. First thing is that. Second thing, it has to be a minimum of these two values. So it has to be a minimum of D0 ij, which is D0, because I am working with my D23, so it will be D023. So D023 is 1. Sorry, D023 is infinity. D023 is infinity. And D0i1 plus D0ij, 1j. Where is this 1 coming from? This 1 is coming from here. Because we are working with 1, we are saying, okay, you are going from I to j, you go through 1, you go from I to 1, and then you go from 1 to j. And find those distances in the D0 matrix, add it up, and whatever is the minimum, take that. So if we do that, then we say that D021 for this, and D013 for this, and those two are 2 and infinity here. D021 is 2, and D013 is infinity. So 2 plus infinity is infinity. Minimum of infinity and infinity is infinity. So I will retain infinity in D123. Let's see D124, because there is some calculations that would be visible here. And that's all probably I will do, because otherwise this will get too lengthy. It is just algebra here that we are trying to do. There is no brain here that we are applying. So I will just keep it at that, and I'll leave it for you to probably practice it out. So D124 is the minimum of D024 and D021 and D014. So D024 is the minimum of D024. D124 is the minimum of D024. And as I said, everything here is D0. So D124 means D024. Firstly, blindly you put whatever is here, there, just change D1 to D0. And then just do a 2-1 and a 2-4. Sorry, 2-1 and a 1-4. 2-1 and a 1-4. So just do a 2-1 and a 1-4. Just like this, 2-1 and a 1-4. And that is the formula. And when you do that, D024 is 4. And D021 is 2. 2 and D014 is 5. So you got a 7 here, minimum of that is 4. That's it. That's all we will do. The rest of the things you are aware of, we have calculated this, we will be calculating this, and therefore we get this matrix. Right, now the placeholders can be filled. Now the next thing for D2, same thing we'll do. The formula is the same. D2ij, everything will be calculated from D1, and this will be copy pasted here, only D1 will change, and you will say Di2 and D2j, Di2, D2j, right? So that's what this formula says. And what we'll do, because we are working with D2, we will take these two columns, keep it the same, we'll keep the diagonals the same. So that's why our working matrix is these two columns are the same, the diagonals are the same, the rest are the stuff we are worried about to fill up. This is the rest. Again, the same concept, same formula application. I'll not go to the details of that. Once you are done, fill it up, you will get D2. Once you have D2, if you are going into D3, then again, because you are going into D3, you will need to have the third row, third column blocked, that is copy pasted, third row, third column, and of course the diagonal also copy pasted. The rest of the rows, cells, you will actually find out the value. How? Using this formula. What is this formula? We know that same formula. We will assume that because we are calculating D3, everything inside will come from D2, and we will just copy paste this, change this to D2, right? And then we will take I3, Di3 and D3j, Di3, D3j, and that's it. And then with that, if you do, you will get the individual cells, put it here, you will get your D3. We have to go till D4. Why? Because we have 4 vertices. That's why we have to go till D4. In D4, this is our starting matrix. So D4 we will block, diagonal we will block, D4 we will block, diagonal we will block. We will not calculate them. Only these are left. So we will calculate them. That's the way to calculate. How do you do it? D4ij. Everything that we want will be coming from D3, right? And then D4 will become D3ij. Copy paste this here. Just change the index. And it will become I4, 4j, I4, 4j. right? So that's the formula. Apply that to those blank cells, you'll get this matrix. This is your final all pair shortest path matrix. This is what you need to produce. As I said, rare chance this will come, but this is how it is done. Maximum chance this will come, and it's a very simple algorithm. We have to take 3 loops because we are working on the row columns, and we are also working on that k value, and that k value is that value which is actually shifting the weights, which means that this is this I4, this 4 is actually the k, right? So ik kj, that is what is happening here. So other than ij, this 4 is actually coming from ik kj. So that means you have 3 loops for k, j and I. J and I are for your rows and columns, and k is the dimension of the matrix you are trying to create. And this is the formula that you know. This is the same formula I've been applying, and that's it. That's the formula. That's the algorithm. So if you see here, this is of order this is of order n. This everything here will run with an order of sorry sorry for that. So this, we were here, it just went up, my bad. Okay, so we were here. So this will be order of n. This everything inside, because of the outer loop, will be an order of n. As you can see, there are 3 for loops. It's going to be order of n only, right? But then I am too pedantic about letting you know how that happens. So let me do it with the algorithm here itself. So this is order of n. This is, because the outer is order of n, everything inside is an order of n. And the inner also executes n times. So everything inside executes that many number of times. This inner executes n times, everything inside executes n times. So this is your highest denominator or highest dominant term, which is going to give rise to an order of n cube. So that is the reason why you have that. That has been explained in this time complexity discussion, and that's how you get an order of n cube. Now, which of the following algorithms solves all pair shortest path? You know about that. All pair means Floyd-Warshall will be the answer. Describe the Floyd-Warshall algorithm. Prove that the time complexity is cubic. We have done that. Solve the APSP problem. I think I told you 2011 once it came. It's actually 2014 that it came. But then this is a huge problem, and it came for 5 marks only. I don't know what they think when they give such problems, but this is your calculations that you will have to do. I've already done that, kept it here. Of course, I'll not be discussing it because it is very mechanical process I just now explained to you. And that is all that I wanted to discuss about shortest path. We have discussed 2 methods, 2 classical methods. One, single source shortest path, Dijkstra algorithm. One vertex to any other vertex, Floyd-Warshall, any vertex to any other vertex. And that will help you crack a lot of algorithms. Thank you so much. Till the time we meet next, happy learning.